Hello, Mr. Lopriato here. We are looking at the basics of bonding, and in this video, we are going to talk about orbital hybridization. All right, so we should feel comfortable with Lewis structures and the VSEPR model and the notation for the VSEPR model. So now we're going to look at the orbital hybridization. All right, so just something to keep in mind. S and P orbitals are going to hybridize. They're going to blend together, essentially. Now, the S is a sphere, the P is a dumbbell. There's three orientations of it, X, Y, Z. And what's going to end up happening is when these two types of orbitals blend together or hybridize, they're going to make this balloon-like shape, right? It'll have a small node on one side, but really it's just kind of in one dimension, all right? And something I want you to keep in mind, all hybrid orbitals, we're going to use a lot of terms, all hybrid orbitals look the same. It's like that balloon shape. So however many orbitals we start with, that's how many hybrid orbitals we're going to get. So in this picture, we have one s orbital with three p orbitals, right? That is a total of 4 orbitals. When they blend together, when they hybridize, we are going to get 4 sp3 orbitals, right? And the notation is just going to list how many we started with. 1s, 3 p's, sp3, right? 4 unhybridized orbitals, 4 hybridized orbitals, right? So they're going to change a little bit, all right? Now, if we are confident in counting the number of electron domains, right? So that would be bonding atoms or lone pairs, all right? The number of domains correlates with specific hybridizations. 2 domains is always sp hybrid, right? 3 is always sp2, 4 is always sp3, 5 is sp3d, and 6 is sp3d2, right? And they have those electronic geometries, right? Linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, and octahedral. All right, so again, the number of domains we will see as the number of s plus p plus potentially d orbitals, all right? So sp3d2, if we were to add up 1s, 3 p's, 2 d's, that gives us 6. That's how we know we have 6 domains. All right, so what is happening? We're going to look at BF3, boron trifluoride. If we look at boron as the central atom, it's AX3. That is 3 electron domains, right? So it's sp2 hybridized. So it has that trigonal planar shape. All right, so why is it sp2 hybridized? This is what boron's electron configuration would normally look like. 2s2, 2p1. All right, now for electrons to be part of a chemical bond, they need to be unpaired. There's going to be orbital overlap. So what's going to happen is those 3 electrons are going to blend together and they're going to make 3 sp2 hybrid orbitals, right? We start it with 3 electrons, so we'll get 3 half-filled sp2 orbitals, right? So essentially 1 s orbital and 2 p's, even though that's not where the electrons are in the ground state, are gonna mix together. And the hybrid has more energy than the s orbital, but less than the p. So overall, the hybrid orbitals will have less energy than the unhybridized form. All right, so if we go back and look at the BF3 molecule, each bond has that sp2 orbital half filled from boron sharing an electron with the F atom. All right, so those 3 hybrid orbitals show up. Now let's look at fluorine. If we look at the fluorine atom, its VSEPR notation is AXE3, right? 1 bonding atom and 3 lone pairs. So that is 4 electron domains, right? So 4 domains is going to correlate with sp3, right? 3 p's, 1 s, that gets us to 4 electron domains. So what is happening there? The fluorine atoms, they are 2s2, 2p5, all right? And there's 7 total electrons there. Well, those 2 types of orbitals are going to blend together, right? We're going to get 4 sp3 orbitals. These 4 orbitals are identical to each other, and they are at a higher energy than the 2s, but a lower energy than the 2p. So overall, the sp3 orbitals will have less energy than the unhybridized form. Now, fluorine's 7 electrons are still going to go into those 4 boxes, right? So 3 of them will be filled up. Those are our lone pairs. And the one half-filled orbital, the one half-filled sp3 hybridized orbital, will overlap with the half-filled orbital from boron, right? So in the BF3 example, boron is sp2 hybridized. One s and 2 p's got blended together, whereas fluorine is sp3 hybridized. One s and 3 p's got hybridized. And the easiest way to remember it is just counting the domains, right? 2 domains, sp. 3 domains, sp2. 4 domains, sp3. 5 domains, we now need to move into the 3rd energy level. So sp3d, and 6 domains, sp3d2. All right, and again, it doesn't matter if it's sp, d2, sp3, sp3, sp2, sp3d, whatever we want to call it, right? All of those different terms. Any hybrid orbital kind of has this balloon-like shape. Doesn't matter how many s's and p's we worked with, it has the same shape, and it all has some amount of s characteristic. All right, so it has this S characteristic, and it is that balloon shape, and that is the orbital notation. And again, it correlates with the number of electron domains.